Hey guys, welcome back to another Algebra 2 lesson. Today we're going to look at transformations of functions. All right, so jumping into the lesson, let's launch this over here in our Algebra 2 textbook. We're going to begin with a warm-up, so take a second, pause the video once the screen pops up there, try these problems, and then unpause to check your answers. All right, so we're going to show the answers now. We have moved 2 units to the right. So if I'm moving to the right, that's going to change my x-coordinate. So notice it went from -1 to +1. The y-coordinate stayed the same. Again, horizontal, we're going to change the y-coordinate. So we went from -1 down 6 units because we went to the left. So -1 minus 6 would be -7. A vertical translation is shifting it down 5 units. So it went from 4 down 5 and stopped at -1. A reflection across the x-axis. Now think about that. It's a reflection. So if it's at the -1, 4, it's up here, and it's reflecting across the x-axis. So the x-coordinate is going to stay the same, but the y-coordinate is going to become the opposite. And with the reflection across the y-axis, the y-coordinate is going to stay the same, but then that x-coordinate is going to be the opposite. Okay, so let's get started with today's standards. And we're going to try to identify and graph transformation of functions, hence the title of the lesson, Transformation of Functions. Some key vocabulary words that we're going to learn today. You can take a second and pause the video if you want. There's a lot of words on here, and I have been making a Quizlet of the words. I was hoping somebody else would do it, but I thought, well, it's not going to hurt me to make them for you. So here are the words that we're going to be talking about: family of graphs, a constant function, identity function, a translation, dilation, and reflection. And of course, some of these you've definitely heard before: reflection, dilation, translation. I'm sure these are all familiar terms, maybe even identity function, maybe family of graphs. We've heard the word constant. I don't know about constant function, but we definitely heard the word constant. You should have heard constant function. It's always a horizontal line is a constant function. But anyway, we'll get into that as we get started. So to learn today, we're going to learn about the translations of functions, and the parent function is where we're going to start. So a family of graph includes graphs and equations of graphs that have at least one characteristic in common. So they've got something in common that makes them a family. So the parent function is what we start with, and then it's transformed to create the other members in the family. Kind of makes sense. In real life, we start with the parents, then the parents have children, creating a family, right? So our parent function is what we begin with. Let's say that it's an absolute value function. We begin with that parent function, and then if I shift it up 2 and over 3, I have now a family of graphs. I've got the parent and then this little translated version of the parent function, creating 2 functions that are considered a family of graphs. So looking at this one, the general equation of a constant function is f of x equals a, where a is any real number. So the domain is going to be all real numbers. Notice this is a horizontal line that goes on forever and ever in both directions. So my x values could be any number out there, all real numbers from -infinity up to +infinity. And the range is only one value. It's wherever that line crosses the y-axis. So it looks like we're crossing here at 1. So that is my range. My range can only be 1. Because notice, I'm not up here anywhere. I'm not down here anywhere. Each x corresponds with the same y value, so my range is 1. And this is a constant function. It's when y is equal to an exact number, resulting in a horizontal line. The identity function is just y equals x, f of x equals x. It includes all the points with coordinates a, comma, a. If I put in 1, I get out 1. If I put in 2, I get out 2. If I put in 3, I get out 3. If I plug in -3, I get out -3. You get the idea here. It's the parent function of most linear functions, and its domain and range, in this instance, both the domain and the range are all real numbers, because any x value I plug in, I'm going to get a corresponding y value. Any y value that I can think of, I'm going to have a corresponding x. So this goes on forever and ever in both directions, covering all x values and covering all y values. All right, absolute value functions. The absolute value function, that's the one I talked about at the beginning. The parent function is just the absolute value of x. F of x is equal to the absolute value of x. It has, it passes through the origin, or it starts, it's at the point 0, 0, and then goes up 1 over 1, up 1 over 1 in both directions. The parent function of a quadratic function is a simple parabola that has a point, goes through the point 0, 0, and it goes up 1 over 1. And think about it. If I go over 2, I'm going to go up 4 on both sides. This is x squared. F of x equals x squared. I plug in a 1, I squared, I get out a 1. I plug in a 2, I squared, I get out 4. Plug in a 3 squared, I'm going to get out 9. Same thing happens on the negative side. If I plug in a negative number and I square it, think about that. A negative times a negative always results in a positive. So we're still going to have positive y values. So my domain here is all real numbers. And over here, my domain is all real numbers. But my range is only, on both of these, starting at 0 and going up. So it's all y values greater than or equal to 0. All right. Let's begin with example 1. Describe the translation in g of x equals x plus 2 squared minus 4 as it relates to the graph of the parent function. So I see this little 2 here, and I'm automatically thinking, okay, it's a quadratic function. If I go back and look, the parent function in a quadratic is y equals x squared, or f of x equals x squared. We're talking about functions, so I need to use f of x. F of x is equal to x squared. So I come back over here. So let's think about what happened here. We added 2 inside the parentheses, and then we subtracted 4 outside of the parentheses. So I know that this happening outside shifts it up or down. Since it's subtracting, it's going down. If it was adding, it would shift it up. What happens inside the parentheses shifts my graph to the right or to the left. And in this case, since it's inside the parentheses, it's the opposite of what we would think it would be. You think if, we're adding, we would shift to the right. But it turns out that it's just the opposite. And if you have trouble remembering that, just plug in numbers and check. Let's plug in a 0. 0 plus 2 is 2. 2 squared is 4. So 4 take away 4 is 0. So when I plugged in a 0, I got out a 0. When I plug in 1, 1 plus 2 is 3, 3 squared is 9, 9 minus 1 is, or 9 minus 4 is 5. So I have a point at 0, 0. Then I have a point at 1, 5. 1, 2, 3, 4, 5. So it's looking like this. We could plug in a negative 1. So I get out 1. 1 squared is 1. 1 take away 4 is negative 3. So when I plug in negative 1, I get out negative 3. And we can keep going. Just keep choosing some values and plugging them in. And eventually we're going to see that we get a graph that has been shifted down 4 units. 1, 2, 3, 4. Because of this minus 4. And then we need to look at it. It's being subtracted by, we have plus 2 on the inside, so it moves it to the left 2. If I add 2, it goes to the left 2. And the reason that the reason that it works backwards of what we would think, this is the original equation. G of x equals f of x minus h plus k, where h tells me if it shifts to the right or to the left, and where k tells me if it shifts up or down. So in this case, since there's a minus h, in order for it to be a positive 2, we know that it must have been minus a negative 2. Think about that for a second. We have a positive 2 in there. The equation should say x minus some number. So in order for that to result in a positive 2, it should have originally said x minus negative 2, which is why it shifted to the left 2. And then we know that a double negative is a positive, so when they simplified it, instead of writing minus -2, they put plus 2. So that's why we shift to the left. And then, of course, this -4 tells me to go down. So my origin, the 0, 0, went left 2 and down 4 units. And there is my point. This point here went left 2, down 1, 2, 3, 4. That's that one that we calculated, -1, -3. Look at my 1. It's up 1, 2, 3, 4, 5. We calculated that point. Once we know where the origin is, we could draw an imaginary line through it and start reflecting those points across so that we don't have to do all the calculations. So, once again, the graph of g of x equals x plus 2 squared minus 4 is the translation of the graph of the parent function 2 units to the left and down 4 units. Guess I was praying. Down 4 units. I don't know. Study tip. Watch those signs. Remember this minus inside of there. So if it's a positive, then it was originally minus a negative. If it is a minus, then we're minusing a positive, so it's a positive movement. So that gets a little bit tricky. Make sure you're understanding that. Example 2. Identify translated functions from graphs. So let's think about this. My parent function would be right here at the origin and go up 1 over 1, up 1 over 1, up 1 over 1. So it looks like we're still going up 1 over 1. So the coefficient of the x didn't change, but it looks like it moved up 2 units and it moved to the right 1 unit. So once again, if this formula is x minus h, to get a positive change, it must have been, let's see here, minus a -1, right? Or no, I'm sorry. We went in the positive direction, so it is minus the 1. See, I told you it's confusing. Minus the 1, because it went in, ignoring the minus sign here, the 1 tells me that it went to the right 1. Okay, and we went up 2 units, so that's a positive 2. All right. Problem solving tip. When using a graph, we're going to write the equation of the graph, then use the key features of the graph to determine transformations. Notice how the maximum, minimum intercepts, and axis of symmetry have changed from the parent function in order to determine which transformation has been applied. So here we can see that this was just a translation. It just slid. It didn't stretch, so it wasn't a dilation. It didn't shrink. It wasn't a compression. It just shifted over and up. Therefore, it's a dilation. So let's talk about dilations and reflections of functions. A dilation is a transformation that stretches it out or it compresses the graph of a function. Multiplying a function by a constant dilates the graph with respect to the x or y axis. So here's my parent function here. And if I make a value of a that is greater than 1, it stretches that linear function upwards. A vertical stretch. Same thing with the v, with an absolute value function. If I make the number in front of the a, like that's in front of what's inside the absolute value, that's kind of like determining my slope or the steepness of my graph. If it's greater than 1, it's going to stretch it upward. And same thing with a quadratic function. The number in front of the x squared term, if it's larger than 1, it's going to stretch it upward. So if my number is less than 1, we can imagine what's going to happen then. It's like pushing a bunch of weight on it. We're pressing it down. We're compressing it. What happens when I push something down? It stretches out. I imagine like taking a ball of Play-Doh and putting a 50-pound weight on it. What happens to that Play-Doh when you look at it? Is it still a perfectly round ball? No, it's flat. It flattened out. It stretched out. So vertical compression is like flattening it out. It's less steep. So notice my graph here, it's steeper. And then when I've compressed it, my A value is less than 1, then it gets less steep. Same thing here. Same thing here. All right, so let's look at horizontal compressions. Okay, when I multiply it by a number that has an absolute value greater than 1, then it's called a horizontal compression. Once again, this 1 over A times my X value, it is a value greater than 1, and it's going to, it looks like it's stretching upward, but it's called a horizontal compression. Okay, and a horizontal stretch is, boom, we're stretching it this way. All right, so let's watch this little video to describe how dilations of functions work. Let's move me out of the way here. Usually these little videos are good.
G of x equals 3x as a dilation of the graph of f of x equals x. To analyze a dilation, start by comparing the function rules. The rule for g of x is 3 times the rule for f of x. Next, identify the type of dilation. The equation can be written in the form g of x equals a times f of x, which indicates a vertical stretch or compression. Because the value of a is greater than 1, the dilation is a vertical stretch by a factor of a. Check by graphing. Apply the steps to another function. The rule for g of x is the rule for f of x evaluated for 2x instead of x. The equation can be written in the form g of x equals f of the product bx, which indicates a horizontal stretch or compression. Because the value of b is greater than 1, the dilation is a horizontal compression by a factor of 1 over b. Check by graphing.
All right, so that kind of sums it up for you, helps you know what you're looking at. We're looking at the x coordinate. To find the new x coordinate of this point, what they did was they said, okay, take whatever the x coordinate is and multiply it by 1/2. Think about that. If I have 2, 2 times 1/2 is 1, and it moved it over 1. So that's what that's explaining. So let's try example 3 with vertical dilations. Describe the dilation and reflection in g of x equals negative 2/5 x as it relates to the parent function. So here's my parent function, y equals x. We knew that this should be, this is a linear equation, so the parent function should just be y equals x, or f of x equals x. Okay, so when I plot this negative 2/5, I started, in my mind, I think, okay, start at 0, 0. I go up 2 and over 1, 2, 3, 4, 5 to the left because it's negative. Or I can go down 2, which is negative, and right in the positive direction, 5 units, because a negative over positive is still a negative. So that's how we can graph the line. So it's important to realize that all that happened here was we took this parent function and we times it by negative 2/5. Okay, so if we think about that, this negative 2/5 that we times the f of x by, if the function is multiplied by negative 1 and the constant a, after it has been evaluated, we say that a has to be between 0 and 1. And it is, because the absolute value of negative 2/5 would be 2/5. The graph is compressed vertically and reflected across the x-axis. So a reflection took place and a compression. So the graph of g of x equals negative 2/5 is the graph of the parent function compressed vertically and reflected in the x-axis. All right, so we're going to stop this video there for today, and we will begin tomorrow with example 4.